Okay, so today we're going to hear from Dr. Frankie Zhu, and she is a tenure track assistant research faculty at University of Hawaii at Manoa in space systems field, and the deputy director of the Hawaii Space Grant Consortium. Her research interests are dynamics, controls, system engineering, and machine learning for space applications. She strives to explore and learn about our universe through and beside intelligent robotic systems. She received her Bachelor's of Science in Mechanical Engineering into 2014 and a Master of Science in Aerospace Engineering in 2017. Received a PhD in Aerospace Engineering in 2019, all at Cornell University before coming to us here at University of Hawaii. And in addition to all of that, Frankie is also one of the co-ambassadors for the Women in Data Science Hawaii this year. And we're very happy to have her involved in that and happy to have her give a talk today on autonomous robots traversing extreme environments.
Thanks, Laura. And Laura is also a co-ambassador for the WIDS conference happening in late April. So thank you for all that you do. So as Laura said, I am Dr. Frankie Zhu, and it's almost exhausting to go through all of my affiliations, but I do a lot of interdisciplinary research. So what comes with aerospace engineering is the fields of mechanical engineering, electrical engineering, and delving into more earth science and planetary science. And now I'm affiliated with the Information Computer Science Department. So thank you for having me. This also acts as a dual talk to have the ICS faculty be exposed to my research. Yes, and I'm also affiliated with Hawaii's Spaceflight Lab, which you'll hear a little bit about later. And I'm the Deputy Director for the Hawaii Space Grant Consortium, which I'll also talk about. So the research I'll discuss today is a very broad overview about my research, which is about how autonomous robots traverse extreme terrains. And then after my research, I'll tell you about some resources on campus that students, faculty, and staff can utilize as a part of the blossoming aerospace community here. Okay, so some of you may not know me. I started in January 2020, but for those that don't know me, I think it's good to know a little bit about my context. I've been to a lot of places. I lived in a lot of places. I was born in Texas. I had a lot of my childhood in Boston, and then a stint in Kansas for high school. And then, as Laura was saying, all of my degrees were at Cornell, which was in Ithaca, New York, which is not the city. It's very rural. And I spent a little bit of time in Los Angeles on a fellowship. So yes, those are my academic stats. My concentration was in dynamics controls and systems engineering and a minor in computer science. And for hobbies, I love eating food. I love rock climbing. I love podcasts and book clubs. And since moving to Hawaii, I also now love paddleboarding. What you'll see here on the right, this is my brother, and we are on the top of Mauna Loa. It was a cloudy day. It was a really strenuous hike, a stage 2 joy kind of hike, and we didn't get a view, but it was awesome. Here's my entire family, my dad and my mom and my brother. And this is us in the Big Island when they were helping me move out here. And they're both academics. Here they are when they were younger, when they were postdocs, and here I am posing next to them. So yeah, that's a little bit about me. So, okay. Prior to coming here, my PhD included a lot of different things. On the top left, for my PhD, I developed a docking technology using magnets and superconductors. The culmination of my work was when we flew in microgravity and demonstrated successful docking in zero gravity. These flights are lovingly referred to as the vomit comet, and I can tell you that I got the authentic vomit comet experience the first time that I flew. You can see more of that work in my job talks posted on my website. So working clockwise on to the top right, hopefully this video will play. I worked on a side project with Dr. Zach Manchester, who launched a small satellite filled with even tinier small satellites, the size of about a cracker. And that's what you're seeing here. This satellite is about the size of a loaf of bread, and these chip satellites are about the size of a saltine. And what's really innovative about this perspective is that typically we see satellites that are very large and have a lot of power dedicated to that one satellite, but this is a distributed system. So what are the missions that are opened up because of this change in mentality? And that's us working on integrating that satellite. On the bottom left, that is a time lapse of a about 1/2 meter by edge length cube, about 50 kilograms. This satellite's name was Violet, and her job was to be the most agile, declassified satellite. And what was really interesting about her is that inside of her chassis, there were these actuators called control moment gyroscopes, which can impart a torque stronger than other actuators. So that's where we can get the agility of pointing and tracking missiles very quickly. And that was funded by the Air Force Research Lab. Yeah, and then here, the last thing I want to talk about, I also worked on something called the Breakthrough Initiative, which is the idea of sending a satellite to our most proximal exoplanet. Yeah, and there are a ton of really interesting dynamics and control problems embedded in all of these different projects. But when I got to Hawaii, what I really wanted to do is leverage the geographic advantages here. So in Hawaii, on the Big Island, there are planetary surface analogs that really mimic lunar and Mars analogs. So I am going to use my dynamics and controls backgrounds to do more so planetary surface robots. So here, I'll set the scene. This is a picture of Curiosity temporarily stuck in sand. And Curiosity's journey is seen here since landing. Since landing, Curiosity has traversed a diversity of terrain: sand, ice, uneven surfaces, slopes of varying degree to get to this vista point, Vera Rubin Ridge, which is where Curiosity took this picture. So I'm interested in autonomous robotic exploration on extreme terrains, particularly for aerospace applications which stress limited resources and safety critical operations. The Mars rovers are prime examples of this type of research, but analogous problems are also here on Earth, such as search and rescue for military or natural disaster relief. Exploring extreme terrain is important. It's relevant for search and rescue. It's also relevant for planetary exploration, as the most scientifically interesting destinations are also the most difficult to reach. But also, exploring extreme terrain is difficult. It's hard to track a trajectory with your robot. It's hard to simulate the terra mechanics, which is the interaction between your terrain and your robot, especially if you're in unseen, unmapped terrain. Sorry, my computer is working on the slide transition. Okay, here we go. So this is a video that I really love to show to illustrate the difficulties of robotic dynamics and controls. So here is a video from the DARPA Robotics Challenge from 2015. And this is a compilation of fails, per se. So there are a number of reasons why autonomous and safe exploration on extreme environments is hard. I love seeing this video, so I'll just let it loop. But these clips properly illustrate how robots must, 1, operate with only partial knowledge, depending on their installed sensors and then their perception algorithms. 2, safely move at speeds related to their dynamics. So you can see here that the bipedal robots in particular have a hard time with reacting in time to their own legs' dynamic modes, whereas the danger for extreme environments are that these extreme environments exhibit friction events, and these events have very fast, very short time scales. So this touches a little bit on terrain mechanics. So 3, robots must account for terrain mechanics or terra mechanics. This includes the unevenness of the terrain due to rubble or debris. 4, robots must make decisions quickly for near continuous motion. There's a lot of processing here happening in real time on board. And when computational processes are simplified at the sacrifice of accuracy, you can have some catastrophic failures. And then finally, robots must be aware of both local motion constraints and global path planning goals. Getting from point A to point B must be broken down into smaller steps that can be acted upon immediately, but also with cognizance of the restrictions of motion or the hazards and obstacles along the way. This is a problem of scales. My proposed solution is to generate interesting waypoints, learn dynamic models, and create control policies online or on site. If we can achieve this, we can not only guard the well-being of our assets, like the Mars rover, but scientists may induce physical traits of the environment from our learned models, which contributes twofold to the planetary science field. Okay, so I'm going to break down the process of autonomous and safe exploration by different bullet points. We're going to start at the beginning, where a lot of space missions are driven by a science goal. And so this is our objective. Viper, which is seen here, is a planned robotic lunar rover by NASA that will be tasked to prospect for natural lunar resources, especially ice, within a permanently shadowed region near the lunar South Pole. The Viper mission is a part of the Commercial Lunar Payload Services program, meant to support the crewed Artemis program, and its launch is expected in 2023. So this robot ideally is going to go out there and map the amount of ice that is distributed in the lunar South Pole. What I am presenting here is one of my collaborators, Dr. Shuai Li in the Hawaii Institute of Geophysics and Planetology, used a satellite to remote sense these locations on the different lunar poles, the amount of hydroxyl that is in the poles, but also these bright cyan dots are places of exposed ice. So from these figures, the community has decided that the lunar South Pole is of most interest, and the science goal of interest is to go in there, land on the surface, and to do some drilling and characterize the distribution of water ice, so that in the future we can use these reservoirs of ice for drinkable water or for propellant and other uses. Now, what comes with that is a really interesting problem of exploration. So given that goal of mapping ice, my job then as a technologist is to think about how to make decisions to explore the space intelligently, efficiently. So here on the top right is the proposed solution that I'm working on that outputs a decision given that we are sampling on the lunar surface in situ and accumulating measurements. So here on the top right is a picture of the lunar surface as we've mapped it from satellites. So this is called a digital elevation map. And here I have in the plane X and Y, and then its elevation Z. The black star is the rover, and its path is outlined in black. So what you're seeing here is the robot is driven by this model. It's called a Gaussian process model. And it's taking in measurements every time it takes a step. And it's incorporating these measurements into the Gaussian process model. And then the Gaussian process model not only models its understanding of the ice distribution, which is over here. The colored surface is the truth, and then the black surface is the Gaussian process model. And what we want to see out of a good model is that gray surface match the colored surface. So the rover is not only learning a model, but it's also generating waypoints based off of its understanding. The waypoints that it wants to propose next are points of high uncertainty. So what we're trying to do here intuitively is to explore the space by going to regions of high uncertainty first, so that we can understand the environment very quickly. On the left and on the bottom right are different metrics that we care about for our model. So with every single sample that the rover is taking, moving, and then taking again, there's a certain variance associated with the model that you can see. At the beginning, we are stressing high variance or high uncertainty samples. And then eventually the model is going to converge to a asymptotic threshold of variance because the model is well understood. And you'll see that reflected in the bottom right for the root mean square of the learned model. So that's one machine learning thing I'm working on. Another thing that robots must do, let's talk about the next step. I'm interested in assessing situational awareness. So instead of suggesting interesting places to go, like I just proposed, this step is more about hazard detection or suggesting paths to avoid to reduce your options. So the picture on the bottom left shows a different robot from a previous mission at JPL called Axel. Axel here is rappelling and traversing a boulder garden on a 30-degree slope in a Martian analog site in the Mojave Desert in California. The boulders are obviously an obstacle, obstructing the rover from moving forward. Another obstacle, though, is, I don't know if you can see it, there's a tether there. So this trailing tether can get snagged between crevices or rocks, or the rover can slip if the tether is on an unstable anchor that deteriorates. This animation on the right is a work of my collaborator, Mike Patton, a roboticist at NASA JPL, who focuses on path planning of tethered rovers. That dumbbell on the top of the platform is our rover, Axel, and the red points, these are different anchors. So once you see this loop, that is our first anchor. And then, so what you'll see here is that if we only rely on that initial anchor to get us down to our goal, which is the black dot here, you'll notice that the traverse path is quite treacherous. Really, the right path to choose is to use that anchor and then pivot around this column to then create a stable anchor, and then in a controlled fashion, lower yourself down to your goal. So that's a flavor of research that I'm interested in and context for my collaborators. The next step in autonomous safe exploration is learning a dynamics model between a vehicle and its terrain. So I'll discuss surface terrain, for which the interaction is called terra mechanics. This diagram here is a free body diagram of the Axel rover that we saw from the last slide. There are many different relationships between the environment and how the vehicle reacts to that environment. These environment parameters, which we'll call theta, could be stuff like gravity constant, the angle of the slope, the static and kinetic coefficients of friction acting on the wheels, the location of the anchor, and on and on. The vehicle's state, which is listed as X here, is its position, orientation, and corresponding velocity terms. This function that predicts the next state also relies on the robot's control input, which could include tether tension and the wheel's motor torques. So with our current state in red, our best guess of environment parameters in blue, and current control input in green, we make a prediction of the vehicle's next state in dark red, shown in this first equation. The act of learning a dynamics model is the act to estimate these parameters and that minimize the prediction error between the state and the measurement that you collect in the field in real time, shown in this equation down here. So just some quick commentary. This is a regression problem. It's a very classic problem with some modifications that are specific to my application. But even more specific to my application, the reason why it's hard is because the model that I want to characterize, this F, I want it to be interpretable. So that means, that suggests a mathematical expression, not a black box. The F of X must be some kind of functional relationship that I can kind of dig in and make inferences upon. Second, the model must be learned in real time at a system level, which suggests equations based on the vehicle state and parameters, and something not like a finite element solution, that I'm trying to stray away from discrete element simulations. Thus, the definition of state has to be at the scale of the vehicle, not at the scale of the granular particles consisting of the rover and of the terrain. And then further, what makes this problem more specific is that I want to use it for an extreme terrain with steep slopes, with potential surface ice, sand, and rock, which is a very hard environment to work in. And it's specific also to the rover geometry. So these environment parameters will differ depending on the robot configuration or morphology. Okay, so the last step of this large process is waiting for the slide. Sorry, y'all. I included a lot of videos, which means that my computer is struggling. Okay, for the sake of time, I'm going to talk through what I'm going to show without the actual graphics. But the reason why this is hard is because there are discontinuous mechanics that are at play. So typically when we look at data, there are certain aspects that we care about, like, is it smooth? And so when I look at my data, sometimes there are measurements where there are discontinuous jumps. For example, places that this occurs are when the rover slips and your velocity profile goes from being like positive to being negative, where you're like slipping backwards. And the video that I had for that was of cars in the snow, which was going to be really funny. Sorry, I'm going to have to restart my presentation. Okay, so this was going to be the video. So discontinuous mechanics or contact dynamics are infamously non-deterministic. Friction and material fractures can cause discontinuities and are inconsistent under the sample initial conditions and inputs, quoted from a professor whose entire thesis was on friction laws and instabilities. So you can see in this video at some point, the car goes from rolling wheels with no slip condition all of a sudden to slipping. It's very hard to model these kinds of interactions. The difficulty then is to select the type of model you want to capture all of these effects. Okay, another difficulty is that there are macro and micro interactions. So what you'll see here is a truck that is trying to drive through sandy terrain. So this is a rigid body. This is a rigid body with rigid wheels, but it's interacting with granular materials that are fluid-like. So at some point in our engineering model to be useful, we need to decide at what scale we want the model to reside. If we choose lengths at the vehicle scale, modeling the grains will be at the sacrifice of accuracy. If we model the grains, we will have to take on an immense computational burden. So this is a trade study on model complexity, how to represent our vehicle state, and what states matter enough for us to include in the model. Okay, and then another difficulty of learning a dynamics model is that we have no training data prior to implementation if we're talking about space applications. We can't test our rover on the moon and iterate, and we have pretty shoddy data from prior missions with different rovers, so we must use transfer learning or some extrapolation of models. Okay, the last piece of this process of autonomous and safe exploration is learning how to control your vehicle in some terrain to follow some reference trajectory. This is called policy generation. So I'll explain in this first equation, you'll recognize a lot of familiar terms. You'll see our current state, which is our robot's position, orientation, and velocities, the environment parameters, the current control inputs, and then here's a new variable. We are also taking in a desired next state as an input to our control policy G. And what this control policy G is trying to figure out an optimal control input for the next time step such that you can track this desired next state or this reference trajectory, which is what this minimization problem is describing. What you're seeing up here is a previous work I did that was creating a control policy in situ in real time with a method called genetic algorithms, where I was trying to find optimal parameters for a state feedback policy. And what you're seeing here is that, so that blue dot is the center of the rover. The red line is the heading of the rover. The green line is the rover steering angle, or what direction the wheels are pointing. And so what you'll see is that at the beginning, we're just using a baseline, very naive control policy, and the rover is struggling to track the reference trajectory on this slippery 30-degree slope, which is one of the steepest slopes in naturally occurring environments like snow or sand. And so while it's doing the baseline control policy, it is collecting some data on its dynamics model and what some optimal parameters would be. And then at some point, the learned control policy snaps in, and the rover is able to track the dotted blue line reference trajectory, which is pretty neat. Okay. But just like with dynamic model system identification, learning a control policy is difficult. The reason why it's difficult is because aerospace is extremely risk averse. So safety is at the forefront of our minds when designing these algorithms. These missions are expensive and we want to guarantee mission success. The consequence is then how to embed guarantees into the algorithm you are creating, or how to prove safety after you've already implemented the algorithm. Big considerations are that we don't want the controller to be unstable and accidentally drive us off a cliff. And so here is a cute video of a Roomba with a very simple feedback control system that prevents it from driving off of a cliff. We also care about optimality when we're crafting our control policies. We care about optimality given when we're in space, we have limited power and computational resources. We need to consider which model and how complex the model is to reduce the computation burden and power consumption to run our algorithm on board in real time. Here is a video of autonomous mining trucks with advanced trailer configurations for which reverse motion is pretty tricky. So an author by the name of Everstedt created a closed loop, rapidly exploring random tree framework, generating motion plans that are not only kinematically feasible, but also include the limitation of the controller's tracking performance when reversing. His method smooths a solution obtained from sampling or some form of graph search using methods from optimal control and optimization. This method, called RT-star, is one of the most widely used sampling-based algorithms for asymptotically optimal motion planning, where we are optimizing for length. That is a design choice, and there are many different models with algorithmic guarantees that have different trade-offs for different applications. Okay, and then finally, we need to consider various terrains. The control policy needs to be adaptable. It needs to change with the terrain that you are traversing. From personal experience, I can tell you that the inability to adapt can cause model bias. So I applied what I thought was the underlying structure of the model. These surfaces represent how correct our model is on the x-axis plotted against various parameters on the, these surfaces represent how correct on the z-axis plotted against various model parameters on the x and y axes. You can call these surfaces loss or cost, derived from objective loss or cost functions. Our learning algorithm tries really hard to traverse the surface by varying the model parameters in the x and y directions to reach a global minimum. But different models exude different surface shapes and minima locations. So if you guess the model structure wrong, you are literally traversing on a different plane. You could converge on a local or suboptimal solution on a different surface because you doomed yourself with a bad predefined model. This is an area of research that I'm really interested in right now, where not only am I exploring loss surfaces, but I'm exploring energy surfaces of dynamic systems, where energy represents the Hamiltonian of a system. Yeah, and if you're interested in that topic, I'd love to talk to you. Okay, so all together now, for safe and autonomous exploration, here are all the pieces. And I'm going to put this in a flow chart so that we can live the life of a robot who is trying to autonomously and safely explore. So to tie all these pieces together, here's the flow plot where we have the different bullet points, but in a state flow diagram. This initial cycle is a little weird, but once we're past initialization, this robot is going to follow the same loop for time step equals 2 to infinity. So as you recall, our very first thing, imagine you are the rover and you just landed on the moon. Before you even open your eyes, you wake up and you feel this internal motivation encoded into your being that says, map out the distribution of ice within this environment, and after meeting some criteria of knowledge, go to the place with the most ice. So that is represented by this highlighted box. All right, so we enter the loop. With this internal drive, you open your eyes and you take in some information. You note your location and you measure the amount of ice beneath you. Then you update your internal model of how much ice is around you. Then you decide whether you want to explore or if you have enough information to exploit your model and just drive to the place with most ice. At the beginning of this journey, you will err on the side of exploration so that you may gather enough information. Then you'll transition to exploitation. It's not always a one-way process though. During the exploitation phase, you could get a measurement that totally surprises you and decide that you have to explore more to resolve the new uncertainty in your internal model. Okay, then you take your first step and you evaluate how close you got to where you wanted to go. Given how close you got, you update your understanding of how your control inputs move your body. You move again, and this is the beginning of the second cycle, which is the loop to enter until the rover you achieve your goal. After you move, you measure your state. Then you update your internal model of how much ice is around you. At this point, you have 2 sample points, and you can start to draw a distribution, at least in the direction of more ice or less ice. With that same measurement, you can evaluate how well your dynamics model predicted your current state, propagating from the previous state. You now update your dynamics model with your best guess of environmental parameters. And simultaneously, you decide to explore or exploit, which gives you the next waypoint. And then finally, to finish the explanation of what your life is like, you evaluate how well your rover tracked that last waypoint, and you update your control input to get to that next waypoint. Thus continues the cycle until you're on the largest ice reservoir in the proximity of where you started, and a good dynamics model and a good control policy. Okay, so I'll end the planetary robotics research topic on this animation of a remote control car that we programmed to track this reference tape trajectory while running the learning algorithm in real time. So at the beginning of the run, the vehicle is running a basic pure pursuit controller, but because the trajectory is a circle, the control doesn't seem that different. A difficulty in robotics is to connect the algorithm to the real rover, which has computational limitations that could affect the speed of which your brain can think, which could affect the stability or reaction time that your rover can act. This will become even more pertinent in steep slope environments where the dynamics have smaller time constants. The reason why I'm showing you this seemingly underwhelming video is because your algorithms have to work in real life. In real time is immensely tedious, but it's incredibly important. So I'm of the philosophy that I need a hardware demonstration to be convinced that the underlying algorithms are useful. Okay, speaking of hardware and rovers, did you know that UH Manoa now has an undergraduate rover team? The undergraduate rover team, also known as VIP Team Rose, aims to compete at the International University Rover Challenge in Utah in June. The challenge is fashioned after the past and future Mars rover missions, where there are science, manipulation, and autonomy tasks. This team is led by Baylor De Los Reyes and Michael Mori, seen in the top left, who are phenomenal undergraduates that founded this team. We have over, I think the last count that Michael told me was 42 students from various backgrounds working on subsystems like the robotic arm, autonomy, instrumentation and control, science, and suspension. On the bottom left are Brett and Ashton testing out a stereo depth camera. On the bottom right is Mackenzie demonstrating how to detect extant life with payloads. And on the far right is a prototype of a rover driving through the hallways near our lab in HIG 314. Okay, outside of dynamics and controls, I'm also passionate about educational accessibility. From a 2012 study, only 78 universities in the US have aerospace programs, which includes subspace. There are about 637 ABET accredited US universities. So that means that only 12% of ABET schools have aerospace programs. Many states, 24 out of 52 states and territories, do not have an aerospace program at all in their state. So I got funding from a NASA space grant to create a low-cost satellite kit that could be used for a variety of space applications. And the goal is to distribute these kits to the different states that are not able to participate in aerospace programs because their state can't support it. So here is a picture of the kits that we're giving to our partnering universities, and here it is as built. The kit itself is supposed to be educational. It comes with a curriculum. It's space flight ready, which means that you can send this CubeSat as built to outer space without having to go through the rigorous process of validating it yourself. And it's low cost. So the kit is aimed to be less than $5,000 USD to make them accessible for a range of different classrooms. On the top right is our mission patch that the wonderful Caitlin Vicuña designed for us. There's a ton of Hawaiian symbol. Yes, there are a ton of Hawaiian symbols in here. That's a CubeSat. That is a plumeria. There's the star compass. So this is very much like we're very proud to represent the state of Hawaii in this project and to bring aerospace engineering into different classrooms. Yeah, so here's a little overview of the different kind of course materials. As a part of this curriculum, I wrote a textbook, which you can access online. It's an open source public domain textbook that the Office of Educational Resources at UH helped me produce. And then I had a bunch of students put together different lab modules for this CubeSat kit. And here's Caitlin building the satellite in a time lapse. Okay, I also teach a couple of courses. To extend the Artemis CubeSat Kit, I am teaching that curriculum at UH in a class called Space Mission Design. It is a part of the Earth and Planetary Exploration Technologies certificate and also cross-listed in mechanical engineering, but it covers all aspects of spacecraft design. And then currently I'm teaching, I see some people in the audience are a part of the machine learning seminar that I'm co-teaching with Dr. Peter Stowski, which is a guided reading at the graduate level around machine learning topics. I'm also a part of the NSF AI Institute. That was a newly founded institute. It is led by the University of Washington, and the institute aims to transform research and education in fundamental artificial intelligence and machine learning theory, algorithms, and applications, specifically for safe and certifiable real-time learning and control of complex dynamic systems. So I'm really interested in the autonomy and swarms application, but I'll be participating in all of these different educational programs for which we are bringing a lot of them to Hawaii. So what you'll see in the future is that Hawaii is slated to host one of these workshops, and we really hope to get a lot of engagement from you all in the audience. The participants that you will be interacting with are world-class machine learning experts from all of these various institutions. So I'm really excited to bring this opportunity. Okay, how are we doing on time? I think maybe I'll just go through these really quickly. So some resources that I want you to be aware of is that as the Deputy Director for the Hawaii Space Grant Consortium, you should be aware that there are undergraduate research internship and traineeship opportunities where you submit a proposal or your student submits a proposal and then they are funded to pursue that research in time, and there are some travel and supply funds that are also provided. So please go to this website to check that out. I'll plug that we are going to start a graduate fellowship opportunity. So this previous opportunity is specifically aimed at undergraduates and is well established, but we really want to extend that opportunity for graduate fellows as well. I know that HIDSE has a really great fellowship program, and so we kind of want to model HSGC fellowships around that kind of model. Yeah, you should also be aware that at UH, there's something called the Hawaii Spaceflight Laboratory, which supports a lot of science missions in planetary science and earth science, oceanography, the Institute for Astronomy. So know that you have a space flight center in the middle of the Pacific Ocean that you can utilize and collaborate with. We have design, build, and fly opportunities. So what you'll see here, we have a clean room on campus where we can integrate satellites that go into space. We have facilities to test satellites so that you can verify their performance. We have ground stations such that you can communicate with your satellites once they're in orbit. And at some point we had a launch facility that we are, that's on the download right now, but will be revamped. Yes. Okay. We're actively working on spaceflight missions. Neutron 1 was, here's a time lapse of it being integrating. It's in space right now and it's still communicating with us. We are also working on something called HITIDE, the Hyperspectral Thermal Imager, which is a NASA mission. And its goal is to test the next generation of high spatial, spectral, and temporal resolution and thermal infrared imagery. It's going to be good for agricultural interests where you're trying to detect the temperature and moisture of the ground. And we are expected to launch in 2022. Okay, to close, thank you so much for your attention. Please get in touch with me. For research, I would love to collaborate on some space robotics project. For courses, I would love it if you signed up for the courses or you had something to tell me about what you need. And then for service, please join the aerospace community and the machine learning community I'm trying to foster. And then say hi. You can reach me at zoo@higp.hawaii.edu. So yeah, thanks for your attention.
All right, thank you, Frankie. And you've left plenty of time for questions. If the audience has questions, you're welcome to unmute yourself and ask questions or type it in the chat. I'll start. Who named Artemis?
Oh, NASA named Artemis. It was, well, it's a follow-on to Apollo. We're going back to the moon, and Artemis is Apollo's twin sister. And I think it's so fitting. Artemis was my favorite goddess when I was in high school.
Mine too. That's why I was curious.
Aw, thanks, Gwen. So good to see some friendly faces or names.
Do any of our fellows have questions?
Ooh.
If I may ask a question, you showed us lots of videos of both humans and non-human driven systems that failed, right?
Mhm.
And you have a good sense of, at this point, I mean, obviously human bodies and any animal body is much better than those robots. But when driving a vehicle, are mechanical systems better than human systems, or not yet?
Yeah.
Or can you see the future better than the rest of us?
It's interesting. So there are many different instances of human performance and robotic performance where there's like a distribution, right? So what we're seeing is that there's an overlap in the quality of driving performance. So, you know, human drivers, they make a lot of mistakes. If we can talk about the autonomous driving revolution, some Tesla cars perform really well in controlled environments, like in Phoenix, where it's sunny all the time. They'll make less mistakes than human drivers. But humans are still much more adaptable. So when it comes to like snowstorms or decreased visibility, then humans, you know, start to take on, they're quite adaptable in those kind of situations. I'll give you some more context. Most of our Mars rovers, for the most part, they are teleoperated, which means that humans are on the other side of the wheel. But we are starting to see bits of their mission operations be autonomous. So there is just like maybe 100 meters worth of distance that the rover is allowed to make its own decisions. But before that, the humans have to check out that the next 100 meters are very safe, are very traversable, well-behaved, for example. Great question.
Truck asked a question in the chat. Truck, did you want to ask it or do you want me to read it?
Could you, I'm doubling Laura, sorry.
You're fine. Yeah. So Truck asked, does the student need to be at UH to apply for the space grant internship you mentioned? Or really, I'll expand to any of those positions that you mentioned. Are they UH specific or UH Manoa specific or?
Yeah, so great question. HSGC, that particular internship requires the student to be a part of the UH system. So it doesn't have to necessarily be at Manoa, but at Hilo, at Windward, Kauai.
Can I ask a question? Sorry.
Please.
Absolutely.
I was just curious, I just wanted to see if you could touch again on your area of interest that you said with particular like loss functions and things of that sort. I kind of was multitasking a little bit, so that kind of caught my attention, and I wanted to hear what you said. If you could maybe reiterate in a few sentences about what the area of interest that you were trying to do in exploring loss functions and whatnot.
Absolutely. So I'll be very upfront and generous with my ideas. I haven't really worked too much into this yet, but for the past couple of years, I've been exploring planetary surfaces. So it's literal space exploration, where your surface is a physical space. But I'm starting to think about exploration of surfaces that don't have physicality to it. So surfaces that are abstract ideas. So a surface in mind that I really care about are energy surfaces that are tied to dynamic systems. So you can think about the total energy of a pendulum, for example, which follows a parabola. Now that's a really simple system. It's convex, it's smooth, but let's say you were able to sample different locations in this surface so that you could characterize the shape of the surface. So it's kind of like you set up your pendulum in an initial condition and then you let it run. So then you have data for that point But then you think about, oh, maybe there are different conditions that, I haven't explored yet that would be interesting and would help me characterize this energy surface. So where next should I set up the experiment? So pendulums are very simple and is a toy case, but think about dynamic systems like think about systems where there are local minima or multiple minima. That in that case, that surface is a little bit more complex, and maybe it would behoove you to explore the parameter space to map out this energy surface, because what you want to know is how your system is going to react in a lot of different cases, in fringe cases. And sometimes you don't know what your dynamics model is when you first start out. Yeah, so that's what I'm thinking about research.
Great, thank you.
Thanks, Jonathan.
Okay, if there are no other questions right now, again, Frankie gave her her email if you guys want to email her. But stay tuned. Next week, we have a talk on context map analysis of consumer voice on social media, a contextualized visualization approach by Dr. Seok-Hwa Hong. And we look forward to seeing you guys there and at many of our upcoming workshops this semester. Thanks and have a great weekend.